Hello everyone, welcome to my second video on curve sketching, and we saw in the previous video the strategy on how to solve curve sketching problems, and we did an example on a polynomial function, a well-behaved function. So here in this video we're going to do the exact same thing, but we're going to look at a rational function and see the difference. So these problems take long, so we're going to go ahead and start right off the bat. So if you haven't seen that video, go back, look at it, and then this over here, what's written in red, is going to make sense. So we have DISA, FDT, SDT, and then sketch. So just recall these domain. I is intercept, S is symmetry, A is asymptotes, FDT is the first derivative test, SDT is the second derivative test. We're going to combine both of those together to create one table, put all our information in it, and then with all that information, we're going to go ahead and sketch this function. So example 1, find all pertinent information on the function f of x equals x over x plus 1, all that squared, and we're going to sketch it. So let's go ahead and start with the domain. So step 1, domain. So what's the domain of this function? So essentially what you're looking for is where does the function not exist? Where do we have issues? Well, we have a rational function, so we have a division, and what can't we divide by? Well, we can't divide by 0. So what value of x here would cause you to divide by 0? So if you're thinking, well, you can't put x as 0, well, that's wrong. Putting x as 0, 0 plus 1 is 1, and 1 squared is 1. That's okay. So what value of x has to be placed in here so that the whole denominator is 0? The answer is x plus 1 squared cannot be equal to 0. So if we square root both sides, so you could go ahead and solve it. This might be obvious to you. You might have the answer right off the bat. But going ahead and solve for it is probably the easier way to do it. So we square root both sides, we get rid of the square, we get x plus 1 cannot be equal to 0. Bring the 1 over, x cannot be equal to negative 1. So here, the function is defined for all values of x except at negative 1. How do we write that? Well, we could write the domain as x is an element of R, all real numbers, and then we use this notation except. So without the value in squiggly brackets, in parentheses, negative 1. So this is, the x is defined for all real numbers except leaving out excluding negative 1. Another way of expressing your answer is x is an element of negative infinity to negative 1, excluding negative 1, union from negative 1 to positive infinity. So all values except negative 1. Okay. Both these notations are equivalent. I would go with this one, but at the end of the day, both are correct. Okay, so this is the domain. It works for all real numbers except for negative 1. 2. So domain is done. Let's go with I. I is the intercept. Let's go ahead and find our intercepts. So we start off with the x-intercept, which recall we solve it by letting y equal 0. Set y equal to 0. So we replace our f of x or our y with 0, and what we get is 0 equals x over x plus 1 squared. And to solve this, we could essentially cross multiply. Multiply this up here, multiply this up here. What you get is 0 times x plus 1 squared equals x times 1. 0 times this whole thing is 0, and x times 1 is x. So we get the value x equals 0. So we have an x-intercept at 0, meaning that this function here is going to pass through the point 0, 0. Okay. Let's go ahead and solve for the y-intercept. Let's do that down here. How do we solve for the y-intercept? Well, we just replace x with 0. Set x equal to 0, and we solve for y. So replacing all your x's with 0, what we get here is f of x equals 0 on top over 0 plus 1 squared. This is equal to 0 divided by 0 plus 1 is 1, 1 squared is 1, 0 divided by 1. Is that an issue? Do we have an issue here? No, so it's not the same as 1 divided by 0. If you're dividing by 0, that's an issue in math. 0 divided by a number, that's fine. 0 divided by anything is just 0. So this is just the value 0. So we get the fact that the y-intercept is at the point 0, 0, which we already knew from the x-intercept. So essentially this function here is passing through the origin. That's the information I was given. So we finished the domain, we finished the intercepts, that's done. What we have next is to check for symmetry. Let's go ahead and do that. So to check for symmetry, we're gonna substitute x with negative x. Okay, so we're checking for even functions and we're checking for odd functions at the same time. So substitute in your function all your x's with negative x, see what happens. So on top, the x gets replaced with a negative x. On the bottom, we get negative x plus 1, all that squared. Okay, so is this equivalent to this? Well, no, because we have a negative on the top. So it's definitely not even, because an even function, when you substitute your negative x into the original function, you get back the original, which is not the case here, so it's not even. Is it odd? Well, odd says you get negative what you started with. Well, we have the negative over here in front, but is it negative of this? Well, no, because here it's x plus 1 squared, and here it's negative x plus 1 squared. And you might be thinking, what if you square it? Well, if we expand this out, what we get is x squared minus 2x plus 1. Whereas this, if we expand it out, let me just show you down here, x plus 1 squared, it's clearly not the same. X plus 1 squared is x squared plus 2x plus 1. So it looks almost identical, but notice here we have negative 2x, here we have positive 2x. Because of that, it's not the exact same thing. So symmetry, there are none. We don't have even functions, we don't have an odd function. So symmetry, none. That's done. So now let's go ahead and check for the asymptotes. So let's go ahead and solve for the asymptotes. We're going to begin with the vertical asymptote. So the vertical asymptote, what you're looking at, the candidate value is the value that's not defined. So we know the function is defined for all real numbers except at -1. Well, what's happening at -1? Do we have a vertical asymptote, or do we have potentially just a hole in the function? So we're going to check at this value -1. One way of doing this is substituting the value directly into the function. So if you substitute -1 into the function, what do we get? We get -1 over -1 plus 1, all that squared. This gives us -1 on the top and 0 squared on the bottom, which is 0. Since we have -1 divided by 0, we have a vertical asymptote, because I told you that whenever you have a number over 0, this corresponds to a vertical asymptote. Whereas if you would have got the indeterminate form 0 over 0, then that's not a vertical asymptote, that's just a hole in the graph. So in this case here, we have a vertical asymptote. This isn't really rigorous. Let's go ahead and solve it the rigorous way. So this is one way you could just convince yourself. But what I would do is check the value of -1 to the left and to the right and see where the limit occurs. If the limit goes to infinity, then we have a vertical asymptote. So check limit as x tends to -1. To the left of it, what's happening to the left of it of the function, and check the limit as x goes to 1, slightly -1, slightly to the right of it, so on the positive side of the function. So let me substitute the function in, x over x plus 1 squared and x over x plus 1 squared. Okay, so if we substitute -1, let's start off with the function on top. We substitute -1 on the top, what we get is -1 over -1 plus 1 squared. So on top, since we're doing -1 but slightly to the left, you should be thinking of a value like -1.00001 or something that's really close to -1 but slightly smaller. So that's -1, and on the bottom what we have is -1.0001 plus 1. So we have a value that's negative, that's really close to 0, but then we're squaring that value, so it turns it positive. So what we get is a negative value on top, and we get, because it's squared, a positive value on the bottom, a value that's really close to 0. Since you're doing a negative divided by a positive, what you get is, well, a positive number that's really close to 0, so you're essentially dividing by a very small number, makes the whole thing big, giving us -infinity. So slightly to the left, we have -infinity. So we have a vertical asymptote. This is valuable information. Let's check what's happening slightly to the right of -1. So if we plug in -1 slightly to the right, so we're thinking now of a value like -0.99999, I'm going to write -1, but really we're thinking of -0.9999. What happens here? Well, if I plug in -0.99 in here, we get a negative value, sorry, we get a positive value, because +1 is bigger than -0.999, and then we're squaring it, so it becomes positive again. So we have a negative number on top, and we have a positive value on the bottom, a positive value that's really close to 0. So again, this is going to -infinity. Okay, so we have a vertical asymptote at -1, and the left and right side both go to -infinity. Valuable information here. So that's the vertical asymptote. Let's go ahead and look at the horizontal asymptote. So the horizontal asymptote, let me just erase this. I'll abbreviate it as HA. We have a trick. We take the limit as x goes to ±infinity, and and we have the function x over x plus 1 squared. So when we take the limit as x goes to infinity, what we're going to do is expand the bottom. So on the bottom, what we have is x over x squared plus 2x plus 1. And all we have to do, using the shortcut that I mentioned, is look at the exponents. We saw this at the beginning of the semester. Looking at the highest exponent of the numerator and the denominator allows us to answer this question immediately. So we know the highest exponent of the numerator is 1, the highest exponent of the denominator is 2. Since the bottom is bigger, the exponent, or the degree, is larger on the bottom than it is on the top, so the highest exponent is bigger on the denominator. This whole thing just goes simply to 0. It goes to infinity faster on the denominator, which means it's going to 0. Okay, so the horizontal asymptote to the left and to the right is 0. So I just want to mention, if this isn't rigorous enough, you're not convinced, the proper way to solve this is to take the limit as x goes to positive and negative infinity. What you're going to do is do x over x squared plus 2x plus 1. And the trick is to divide by the highest exponent of the denominator, or to factor it out, doesn't matter how you think of it. So let's divide by the highest exponent of the denominator, the top and the bottom. What we get is limit as x goes to plus minus infinity. We have x over x squared on the top. So the highest exponent of the denominator is x squared. So we're going to divide the x on top by x squared, and we're going to divide the whole bottom by x squared. This gives us limit as x goes to plus minus infinity. On the top, what we're left with is 1 over x. You subtract the exponents because there's a division. All that divided by, here I'm going to divide each term individually. X squared divided by x squared is 1. 2x over x squared is plus 2 over x. And lastly, we have 1 over plus 1 over x squared. Okay. You have to remember the theorem that the limit of any number divided by x as x goes to infinity is 0. That's one of the theorems that we saw at the beginning. Limit as x goes to infinity of any number over x. And x could have an exponent, doesn't matter. So you're dividing by a very large number, the whole thing goes to 0. Using that argument over here, this theorem, the top goes to 0. Here we have 1, 2 over infinity is 0, and 1 over infinity is 0. So we get is 0 over 1, which is 0, and that corresponds to the answer that we got up here using our shortcut. Okay, so this is the more rigorous way of solving the problem. So we finished the asymptotes, that's done, and this leads us into the next step, the first derivative test / second derivative test. We'll do them both together in one shot. So let's begin by finding the first derivative. So we're going to take the first derivative set equal to 0. We're looking for the critical numbers, or the critical values. Here we have a fraction, so we have to apply quotient rule. So we're taking the derivative of the top. Let me just remind you guys. Quotient rule, f divided by g prime, it's the derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared. So the derivative of the top is 1 times the bottom, we're going to leave as is, minus, because it's quotient rule, the derivative of the bottom is 2 times x plus 1 times the derivative of the inside, which is 1, and then times the original function on top, the numerator, times x. All this over the bottom squared. So x plus 1 squared, all that squared is just x plus 1 to the 4. So let me write it this way. So before I proceed, let's simplify. So I notice on the top that the left term and the right term both have an x plus 1. Let's factor one of them out. So what we get is x plus 1. We're left with x plus 1, because here it's squared, so we take out one of them, we're left with another one. Minus, we took out the x plus 1, so we're left with minus 2x. Over x plus 1 to the 4. So we have x plus 1 over here, we have x plus 1 to the 4. So one of them cancels with one of them in the exponent, leaving us with 3. And on the top, what we have is x minus 2x, that's negative x, so 1 minus x over x plus 1 cubed. This is our first derivative. Now that we have our first derivative, we set it equal to 0. Okay. So since we have a fraction, we know that the critical value occurs when f prime of x is equal to 0 and when f prime of x does not exist. So the two cases is we look at the numerator and we look at the denominator. So numerator, when f prime of x equals 0, what we get is 1 minus x equals 0. Bringing over the x, we get x equals 1. So we have a critical point at x equals 1. The other case that we have is to look at the denominator. Looking at the denominator, this is the case where f prime of x does not exist. It occurs when x plus 1 cubed equals 0, right? Because we can't divide by 0 in math. Cube root both sides, we get x plus 1 equals 0, taking the cube root. And then bringing this over, we get x equals negative 1. Okay. This is a critical point. But notice that x equals negative 1 is where the function is not defined. The domain of the function is all real numbers except negative 1. So there's no point at negative 1. So we can't have a critical value at negative 1. There's no point there. So we're going to exclude it. We're not going to use this one. We're just going to use x equals 1. Okay, so that's our critical value. So we got our critical point, x equals negative 1. X equals positive 1. That's our critical point. And now let's take the second derivative and find the inflection point right away. So let me just write it over here, erase this. So the first derivative was 1 minus x over x plus 1 cubed. And let's go ahead and find the inflection point. So the second derivative, and we're going to set it equal to 0. So again, it's quotient rule. So we take the derivative of the top, which is negative 1 times the bottom, minus the derivative of the bottom times the top. All that over the bottom squared. So x plus 1 cubed squared just gives us to the 6. So what we could do is factor out an x plus 1 squared. I would always factor out as much as I can. That's always my game plan, to simplify it first. Okay, so don't try expanding this, factor out. So the most we have here on the left hand side is x plus 1 cubed. Here we have x plus 1 squared. You always take the lowest exponent. So we can factor out an x plus 1. Well, we can factor out a negative 1 as well. Might as well do that. So negative 1 times x plus 1 squared. Taking out negative 1 x plus 1 squared, what we're left with is x plus 1 on the top. This turns into a plus because we factored out a negative. And this x plus 1 squared came out, so we're left with just 1 minus x. Okay, over the bottom, x plus 1 to the 6. So if we have x plus 1 squared and x plus 1 to the 6, two of them cancel out, leaving us with 4 on the bottom. So this whole thing's gone. So this is negative 1. Inside the bracket, we have x minus x, they cancel. And 1 plus 1 is 2, and we have a negative in front. So we get negative 2 over x plus 1 to the 4. And that's our second derivative. Okay, so we're looking for the inflection point here, or a potential inflection point. Well, that occurs when the derivative, or second derivative is equal to 0, or the second derivative does not exist, similar to the critical points. So either the numerator is equal to 0, which is impossible because the numerator is negative 2, or the denominator is equal to 0. But again, if we look at the denominator, it's x plus 1 to the 4. So we're looking at the denominator. Solving when x plus 1 to the 4 equals 0, we take the fourth root on both sides to get rid of the 4. We get x plus 1 equals 0, and then bringing the 1 over, we get x equals negative 1. But again, x equals negative 1 is the value where it's not defined on our function. So we can't have an inflection point there. The point's not defined. So we can't have an actual inflection point. There's no point that exists. So again, we ignore this. We don't use it. Okay. And now we're going to use all this information to sketch our graph. So let's go ahead and create our number line. So we have a critical point at 1. This is our CP. And we have a critical point and an inflection point that didn't exist at negative 1, where we know this is where our horizontal asymptote occurs, but we still include it in our table. Okay, and let's see what happens around this value. So we have this negative 1, 1, and let's create 3 lines. So we have our f prime of x, first derivative, we have our second derivative, and then we have the original function. Okay. So let's see what happens in between. So notice that this is our number line, so this goes off to negative infinity, and this takes off to positive infinity. Let's see what's happening in between. So let's test values. So the values in between negative 1 and 1, we'll take 0, it's easy value to test. To the left of negative 1, let's take, I don't know, negative 2. and work with positive 2, greater than 1. Okay, so our first derivative, let's go ahead and use our first derivative. The first derivative was f prime of x equals, it was 1 minus x over x plus 1 cubed. So let's go ahead and test our three values. So f prime of negative 2, plugging in negative 2 here, we get 1 minus negative 2 over negative 2 plus 1 cubed. This 1 minus negative 2 is 3, over negative 2 plus 1 is negative 1 cubed. This gives us negative 3. So when we plugged in negative 2, we got a negative value. Okay, let's check at 0. When we plug in 0 into our first derivative, we get 1 minus 0 over 0 plus 1 cubed, giving us 1 over 1 cubed, which is just positive 1. This gave us a positive, so it's positive on this interval. And over here, greater than 1, when we plug in 2 into the first derivative, we get 1 minus 2 over 2 plus 1 cubed. 1 minus 2 is negative 1, 2 plus 1 is 3 cubed. So we get a negative value. Okay, so negative 1 over 27, 9 times 3. So we get negative, positive, negative. So that's the first derivative done. Let's go ahead and check the second derivative. So the second derivative was, it was negative 2, I believe, over x plus 1 to the 4. Yeah. So we have negative 2 over x plus 1 to the 4. So here technically we don't have to test all the values, because if we put in negative 2, no matter what we put in the denominator, because it's to the exponent 4, it's always going to be positive. So the denominator is always going to be positive, and the numerator is always negative 2. So we have a negative divided by something that's always positive. So this is always negative. So we don't even have to test the points. So it's always concave down. This would be negative, negative, and negative. If you want, you could go ahead and test, but we could see it from the fact that the denominator is to the exponent 4, so it's always going to come out positive, and the numerator is negative 2. Okay, so let's go ahead and see how this affects the original function. Actually, before we do that, let's just locate at the critical points. What do we have? So at negative 1, this is not defined, so I'm not going to worry about it. It's not a critical point, so I'm going to put like an x here. We're going to ignore that. But over here, the first derivative is positive, which means the function's increasing, and to the left, to the right of 1, it's decreasing, it's negative. So we know at 1, this is going to be a local max. Okay, because to the left, the first derivative is increasing, then it's decreasing, so it's like a hill. So this is the top of the hill. We have a local max. Now let's use the fact that concavity here is negative, so we have concave up, concave down. Let's see which of these segments we're using. We cut it down the middle. So here the first derivative is negative, telling us it's decreasing. The second derivative is negative, so it's concave down. So concave down this side and decreasing. So we're using this arrow here. So it's to the left and going downwards. The original function is looking something like that. Okay, decreasing and concave down. In between the interval from negative 1 to 1, the function is increasing. First derivative is positive, so the function is increasing. The second derivative is negative, so it's concave down. So concave down, but increasing. So we're using this segment here. So it's going to go increase and concave down. Yeah. And then lastly, we have a local max. After our local max at 2, we have the first derivative is negative and it's concave down. So concave down and decreasing. So we're back to something like this. Okay. So this is what our function is going to look like. Okay. So the next thing we could do is go ahead and find where the local max actually occurs, because this is a point that the function is going to pass through. So let's go ahead and actually find the point. How do we do that? Take the critical point, 1, and plug it back into the original function. So the critical point, let's call it CP. We're doing f of 1. So plugging 1 into the original function is going to be 1 over 1 plus 1 squared, giving us 1 over 2 squared, which gives us 1/4. So the local max occurs at the point 1 comma a quarter. Okay. So So that's valuable information. So let's keep this in mind. We have our table done. Let's go ahead and sketch the entire function. So here we have our graph, the y-axis, x-axis. The first thing we could go ahead and sketch is the horizontal asymptote at -1. Oh, sorry, not the horizontal asymptote, the vertical asymptote. The vertical asymptote at -1. So that's our vertical asymptote. So the function is not going to pass through this red line. We have a horizontal asymptote at 0. But here we have to be careful. So we have a horizontal asymptote. The idea of an asymptote that we know is that our function never passes this. But this is kind of a false claim. Okay. Let's pretend that's the x-axis. It's on the x-axis. Really what it's saying, when x is extremely large to the left and to the right, then the function will eventually not pass the asymptote. But in the middle, over here, when x is small, or close to the axis, let's say, the y-axis, our origin, the function could go through the asymptote. Okay, so the horizontal asymptote is really when we get really large to the left and to the right. The function's gonna never pass the asymptote, okay? So keep that in mind, because here we have an asymptote, but we know that our intercept is the origin. So even though we have a horizontal asymptote on the x-axis, the function is still passing through the origin, okay? So that's a bit of a trick, so keep that in mind. The next point that we have is our local max. The critical point at 1, let's say 1 here, and a quarter. Let's make this a quarter. So it's going to pass through this point here. This is our local max. Okay. And let's go ahead and figure out the in-between. How do we connect all this together? Well, we saw from our graph that in between, on the interval from -infinity to -1, the function was concave down and decreasing. So for it to be concave down and decreasing, it's going to come really close over here and then go hit very close to the asymptote, something like this. Okay. We also know that we had a vertical asymptote, which next to -1, it went down to -infinity. So it makes sense that we had to the left of -1, it went down to -infinity, and also to the right of -1, it went down to -infinity. So everything so far is holding. Next, it's going to start up over here. And on the interval from -1 to 1, on our graph, it said that it was increasing and concave down. So it was opening up this way. But at the same time, it's increasing concave down, but it has to pass through the origin, and it has to go attain the local max. So it's going to look something like this. Through the origin, and then hit our local max. Okay. And then lastly, on the interval from 1 to infinity, it said it was concave down and decreasing. So it's just going to continue. It's going to remain concave down and just slowly go down forever, but it won't pass the asymptote, right? Because it passed it over here, but as we get really large, it's never going to pass the x-axis. So it's going to look something like this. And this is the function of f of x equals x over x plus 1, all that squared. So make sure when you're doing this, after you finish sketching, go on Desmos, use a computer application software, Mathematica Maple, and just make sure that the function you drew is very similar or resembles what the computer outputs, okay? So just double check your work. So I hope this helps. Keep practicing, very tough topic. We've seen polynomials, we've seen rational functions, try different functions, sketch maybe a function that incorporates sine, maybe exponentials, logarithms, and yeah. So I'll see you in the next video.